Let us now look into the different properties of probabilities. Now, we have assumed previously that all outcomes of an experiment are equally likely. However, in general, this may not be true. A sleight of hand magician might toss a weighted coin. There might be a weighted die in a game so that it will give rather the desired outcome. So we should discuss the notion of probability in general. It's not always an assumption that the outcomes are equally likely. Suppose that a weighted coin is tossed rather, and the chances of getting a head are 65%. So this would mean that the probability of getting a head when you toss that weighted coin is 65%. So the other probability, which is getting a tail, because the sample space of getting a toss coin will just be heads or tails, this would mean that the other is what's left of an entire probability, which will be 35%. Because if the other one is 65%, the other one should be 35 so that it will be 100%. Or the probability that you actually toss the coin. Now, if you might have noticed, this intuitive notion of probability will actually lead us to the definition of a probability assignment. So we define S is equal to the set containing the elements S sub 1, S sub 2, S sub 3 up until S sub k. Be a sample space with k outcomes. A probability assignment is to the outcome S sub I is an assignment of a real number P sub I equals 1, 2, 3 up until k, such that the following holds. So, that P sub I, that real number assignment, that probability assignment is in between 0 and 1. And when we add all those probability assignments, it should add up to 1. So this is telling us that even though we know the events are not equally likely, if we're going to have a probability assignment, all assigned probabilities should be in between 0 and 1. And when we add all of those in the sample space, they should add up to 1. So let's have an example. Suppose a coin is weighted such, so it's a weighted coin. We are given that H and T are the following events. H is getting a head in a coin toss, T getting a tail in a coin toss. And suppose we're given with these probabilities. Now we know, like what we've mentioned just a while ago, in a coin toss, the sample space will just be either heads or tails. So we are complete already here. The probability of getting a head is the 0.53. The probability of getting a tail is 0.47. Both of them are in between 0 and 1. And if we're going to add 0.53 plus 0.47, we're going to have actually 1. So this follows the first and the second requirements. Hence, we can say that this is a probability assignment. Probability assignment. And we can take that the probability of getting a head in this experiment is 0.53, while the probability of getting a tail is 0.47. So let's have another example. Suppose an experiment has 5 outcomes given in the sample space set S containing the elements S1, S2, S3, S4, S5. Suppose that the probability of the outcomes are given in this table. Let us make sure that this is an actual probability assignment. So first, double check if all the probability assignment values are in between 0 and 1. So as we can see, they are. Now, if we're going to add all of them up, will they add up to 1? So we have 0.05, 0.35, 0.10, 0.30, and 0.20. So when we add this is 5 actually here. Let's fix that so it's more visible. There you go. So this is 5 here. So we're going to have here 10. Then that's 3, 4, 5, 5, 10 also, and 1. So all are in between rather 0 and 1. When we add all of them, it becomes 1. So therefore, this is an actual probability assignment. And therefore, we can further analyze what would be the probability of the specific outcomes.